Good afternoon, ladies and gentlemen. My name is Jiangnan Yao. Welcome to my meeting review for achieving large uniform tensile elasticity in microfabricated diamond. Today, I will start with a brief introduction on diamond as a promising alternative semiconductor material and some basic info about the paper. Then I will discuss the doping challenge as the central problem highlighted by the paper, and the author's attempt to solve it with the deep elastic string engineering. Then we will touch about the theoretical mechanism behind the phenomena and how this is significant to the academia and the industry as well. Well, diamond is widely known for its extreme hardness and therefore widely applied in cutting tools, wear components, and etc. However, its extraordinary electronic and thermal properties have drawn significant attention and resources from the academia due to its potential to become the new generation semiconductor material. The high carrier mobility, thermal conductivity, and breakdown field strength have made synthetic diamond a perfect candidate for the potential applications in semiconductor industry, especially where high frequencies, high powers, high temperatures, or high voltages are required. This paper under review, Achieving Large Uniform Tensile Elasticity in Microfabricated Diamond, is one of the most recent endeavors to push the diamond one step further towards the device application. Well, next we're going to explain the doping challenge. Pure diamond, as you can see in this table with a band gap of 5.5 EV, is naturally an insulator, which means it needs to be doped before any semiconducting application is possible. But the wide gap between the valence band and the conduction band has made it extremely challenging to dope the diamond. Despite the continuous trial and errors, researchers have not yet found a perfectly satisfactory N-type dopant for the diamond. And these difficulties, compared to the traditional narrow bandgap semiconductors, can be explained by two primary reasons. First, dopant ionization energies increase with the bandgap, which consequently result in a decrease in the proportion of carriers that can be thermodynamically freed from the bond state. Thus, the UWBG semiconductors material, just like diamond, with their wide bandgap, find it difficult to achieve the minimum free carrier concentration required by many electrical applications. Second, the large bandgap of diamond or other UWBG materials lead to a higher probability of the carriers trapped themselves. Carrier ion localization resulted from the nature of the valence band state of the first row elements creates more self-trapped hole and effectively suppress the electron mobility of the material. Both causes just mentioned for the doping challenge can be explained by the diamond's ultra-wide bandgap, which implies that any method that can effectively decrease the bandgap of diamond may be a potential solution to this challenge. Well, deep elastic string engineering could be a potential solution as it will alter the physical properties of the material, including the bandgap. Diamond have a maximum elastic strain above 9%, which makes it satisfy the 1% elastic strain rule and satisfy the prerequisite for the elastic strain engineering. Given the information, the author designed experiments to put the microfabricated single crystalline diamond bridges to undergo uniform elastic tensile strain. Then a density function theory, a DFT calculation, was performed from 0% to 12%, and an electron energy loss spectroscopy, EELS measurement was conducted as well. The result, as you can see in the figure 1 and figure 2, clearly shows a reverse relationship between the bandgap width and the tensile strain applied. Besides, the figure also demonstrated that the bandgap closure was more significant along the 101 direction, and the critical point between the indirect to direct bandgap transition happens around 9% strain. Along 101 direction and with a 9% strain, the bandgap is tremendously reduced from the initial level of 5.47 EV to 3.09 EV, which is lower than those of the widely used wide bandgap semiconductors material. This huge reduction in bandgap has a significant implication, which we will discuss in the fifth part of this essay. all the properties of crystalline material depends on its lattice parameters and the shape of the unit cell. Unlike the bulk material whose atom structures remains unimpacted by the physical changes, semiconducting nanostructures' electronics properties are subject to change in their shape and size. Particles in the bulk material are considered free, as the confining space is larger than the wavelength particles. Thus, a continuous energy state is observed, and the band gap remains unchanged. However, when the confining dimension is small enough, the quantum effect is triggered, which means that the energy spectrum becomes discrete, and the band gap becomes tunable by the size and the shape of the material. This theory tallies with our observation in diamond nanocrystal, as we discussed in the previous section, and supports a wide range of potential further research and applications based on the strain-induced diamond band gap manipulation. We believe that the research outcome that the band gap of the synthetic diamond can be significantly reduced through the uniform elastic tensile strain is a big step towards the diamond semiconductor for several reasons. First, the doping challenge could be potentially solved, which is primarily resulted from a wide band gap, which can be reduced to ESE. A perfectly doped diamond is believed to be a game-changing alternative as a semiconductor material due to its extraordinary carrier mobility and other awesome characteristics. Second, with the reduced band gap through the tensile strain, diamond has a similar band gap with the mainstream wide band gap material, but with a superior thermal conductivity and electromobility, which you can see in this table, which implies that the commercial substitution is possible using the diamond semiconductor to replace the mainstream WBGs. Third, since the band gap can be tuned based on the strain applied, precise control is possible to be achieved through the ESE. Unlike the predecessor's attempt to apply shear and compressive strain, the uniform tensile strain used in this paper can be more precisely controlled. As a result, a diamond can be adjusted to fit the band gap requested, optimizing the performance of the potential electric devices. As a conclusion, diamond is one of the most promising alternative semiconductor materials, despite all the obstacles we need to clear out before its commercialization. These papers focus on potentially solving the doping challenge with the deep ESE, and we regard it as a significant progress towards the diamond's ultimate commercialization in the semiconductor industry.